This is the Death Star, a weapon used to destroy Princess Leia's home planet of Alderaan in Star Wars A New Hope. For us, this advanced weaponry is only feasible in sci-fi movies. However, we're not crazy in thinking that we can achieve such a high-powered laser destroyer in the near future. In order to understand how a high-energy laser weapon like the Death Star can work, we must first understand the basic operations of a laser. As we all know, when looking at two energy levels, an electron can jump between these energy levels, the energy gap, by absorbing a photon to create an electron-hole pair, or by recombining with the hole to emit a photon. There are three processes that we have to consider: spontaneous emission, stimulated emission, and absorption. Spontaneous emission occurs when an excited electron randomly falls to the valence band to recombine with the hole, emitting radiation in the process. Spontaneous emission does not require photons to be present. However, stimulated emission occurs when an electron is stimulated to fall from a conduction band to a valence band by the presence of photons of the proper wavelength. Absorption, however, is the time inverse process of stimulated emission, occurring when an electron in the valence band absorbs a photon and jumps to the conduction band. Lasing action happens when stimulated emission exceeds absorption. This requires population inversion, which means that the number of carriers in the conduction band is greater than the number of carriers in the valence band. Population inversion can be achieved in a forward bias PN diode when the difference between the quasi-Fermi end levels is greater than the energy gap. In order to provide enough stimulated emission for lasing action, we increase the photon density by using mirrors. A lasing medium inside an optical cavity consisting of mirrors ensures that photons created will stimulate the creation of even more photons. The mirrors need to be spaced by an integer number of half waves to ensure that the photons created will not destructively interfere with each other. By forward biasing a PN junction and increasing the current above a threshold current, the intensity of the output light will be the greatest and the highest gain cavity modes will dominate. With the PN junction at high forward bias, the electrons and holes want to diffuse away from the depletion region, but to make a laser, we need to keep them together. To keep carriers together, we have to embed a lower bandgap layer inside high gap barriers that act as a bucket that traps electrons and holes. This is called a double heterostructure. Typically, gas sandwiches outgas in these types of laser diodes. Though most diode lasers are built this way, there are other characteristics that affect how to build a laser. Many different materials can be employed to build lasers. The so-called diode lasers use semiconductors as a medium. They are characterized by lower power consumption and small size that can be used to read CDs, for example. Other lasers use gas, such as helium, helium neon, argon, and carbon dioxide as their medium. Carbon dioxide lasers emit energy in the far infrared and are used to cut hard materials. The advantages of these lasers include their inexpensive cost, high volume, and their ability to quickly transfer heat out of their optical cavity. Because of these properties, they are often used for tasks requiring high precision. Lasers may also use liquid as a medium. For example, there are dye lasers which use complex organic dye molecules in suspension as a medium. Their main advantage is that it can produce a very broad range of wavelengths and are used primarily in research and medicine. Also, because they use liquid as a medium, they are very thermally efficient. Some lasers use solid-state materials like ruby or neodymium YAG. Their great advantage is that they produce light with high density of energy, but they have the problem of heating up too much. These lasers differ from semiconductor lasers in the sense that electrical energy is used as a pump source for semiconductor lasers, whereas solid-state lasers use light energy as their pump source. This is all fun and interesting, but how can we use this to build a Death Star? Well, turns out the military is using a special type of laser which combines the high energy density of solid-state lasers with the thermally efficiency from liquid lasers to build weapons that can shoot drones down. Maybe laser weapons are not too far off in the future.